My name's Sindre, solutions architect at Graphistry and a former police officer here in Oslo, investigator, and been working at an MSSP. I've been working with Graphistry for a little over 1.5 years now, and I love graphs. So that's what we're going to talk about. Manfred?
Yep, so I also work at Graphistry. I'm a visualization engineer, so my focus is mainly on designing and building graph renders, so the things that make those pretty pictures that you see up there. And yeah, in addition to that, though, I've become a bit of a graph practitioner, so understanding how to use them. So that's sort of along the lines of the things that I want to talk to you guys about today.
Yeah, just go to the next slide. So yeah, a little bit about us and Graphistry and what we do. Just to get it out there, this is not a vendor pitch in any sort of way, because everything we're going to do today is open source for you guys to test, and our product is free to use if you want to use it. If you're government and you can't share anything, then you can pay for it. So, but everything we're going to do and show you is open source, and you can test it yourself. Anything we do with graphs is on GitHub. It's Python, so getting that out there that it's free to use. So Graphistry is built upon Rapids. That's NVIDIA. If anyone's been using Python to look at any data, you probably used pandas or polars or anything like that. And Rapids is basically NVIDIA's solution to run that on GPUs. So you can basically just run everything you're doing on your pandas stuff. You can do it on GPUs by just using QDF instead of pandas. And next one. So what we're going to talk about. We'll try to show you the advantages of looking at graphs over like the other analytical approaches that most of you probably are familiar with looking at data tables in your SIM or your XOR or your source solution or something like that. Basically logs, looking at logs in a different way. And we'll show you some tools that can be used for that. And we'll try to work through a real cybersecurity data set as an example. So going from tabular to graph and select some encodings to make the connections pop and try to extract some answers to that. And basically, hopefully at the end of this session, you have some ideas on how you can use graph investigations on your own data. So yeah, we're going to do it in like 3 sections. We're going to look at small graphs, medium graphs, and large graphs. And we'll try to get you to understand what graphs are. And when we talk about graphs, many people think about diagrams. That's not the graphs we're talking about today. We're talking about connections, basically. So what is a graph? In its simplest matter, it's a set of points with a line between them. So any social network, that's a graph, basically. Who knows who? If anyone's been thinking about or heard about like TV shows where you're like 5 degrees of separation, how many steps are you away from the king of Norway, basically? That is graph questions. So, and for security, why does graphs matter? A couple of years ago, we're back in 2014, John Lambert out of Microsoft put out this tweet, and it was a tweet at that time. So the biggest problem with network defense is that defenders think in lists, attackers think in graphs, and as long as that is true, attackers win. If any of you are on like a blue team side or a red team side, you probably played around with Bloodhound, looking at Active Directory to see how can I traverse, how can I basically become domain admin, global admin, stuff like that. And that's how attackers think. They want to go from point A to point money. And as defenders, we're not there yet. And so why are we still going tabular? Most of the tools are built tabular. Our databases are tabular most of the time. Our logs are basically tabular. Anything that we produce in this community and in cyber basically is tabular by design. And it's great when you're looking at what happened. When you go in and you're looking at a specific problem, it's super good with tabular data. You can aggregate, you can count and search stuff easily. But it's not that good when you want to look at how it happened and what is connected to what. And you're not getting away from AI in this matter either, because with AI, we see a lot more use of knowledge graphs and graph RAG, and basically AI built upon graphs. So many more vendors are actually leaning hard into this now. You have Google created their own graph database for Google Spanner Graph, and Microsoft also, during the fall, they released the Custo Graph for Azure Data Explorer, and they're in preview, as everything Microsoft is, for Sentinel Graph as well. So there's a lot more focus from the big companies as well that graphs are good for cybersecurity, because you need to see the connections. You need to know what person is normally using that device, what resources does this person have access to, etc. And for graphs, I like to think that like one picture that says more than 2 million rows. Because if you want to look at this as tabular, it would be quite hard to see that there's basically two distinct clusters, or many clusters basically, of data, and how things are communicating across those clusters. It's a lot easier. This is just a small sample of 4 weeks of network logs on a small computer, like super small network. So 2 million rows. I'm guessing 2 million rows of network log is an hour in most companies these days. So, it gives you a clearer image of what's happening. It's not impossible to find connections when you're looking at it tabular. Basically it's SQL joins, pandas merge, and when you're trying to go many hops, it becomes quite hard to do that. You need to okay, what's the foreign key here? I need to join, I need to merge. And for graph queries, it's a lot easier, because it's very descriptive what you want to do. When you look at this simple query, it's basically I want to start from a node. Then let's Schumer. I want to go to a different senator, and then I also want to see what senators does Pelosi and Schumer know together. That's the same query we're trying to do up for the tabular one. There you go up, back one. So yeah, it's basically the same query we're trying to do with the SQL joins that we're doing in the graph query down here. And why do we like GPUs for this? Basically, GPUs can handle a lot more. And given that it's built upon arrows, and arrows is columnar based, so it's not searching row by row by row. It's searching first the column, and then it goes and grabs the row if you're searching for something. And to put it like the simple description of or like this, to explain it simply, your CPU might have 8 cores, so it's reading 8 rows at a time. A GPU might have 20,000, so it takes a lot more chunks, and it reads more, and it offloads that to a lot more workers. So if we did a benchmark on this summer, where we were trying to see, okay, how big of a data set can I actually work with and still operate on a sub-second? Like you press enter, you get your response. So if you have a small data set, and small is, what's small basically, but if you're on 1 million connections in your data set, so like 1 million edges, it's not a problem doing that on your CPU. That takes a second to go 3 hops out. Start from one node, traverse everything 3 hops. That takes 1 second. And if you go on and run it on a GPU, like basically the cheapest one, or you can get on AWS or Azure, is a T4 GPU. That's 2018 technology, I think. And then you can go to 100 million. And if you're a rich guy, you can go and rent a H100, and then you can do 2 billion edges in basically the same time. Because if you have a lot more VRAM, you can handle a lot more, and you have a lot more cores, you can basically start looking at a lot bigger data sets and working on a lot bigger data sets. So yeah, what we're using for this when we're starting to demo stuff is we're doing pandas and network X. For the small one, Plotly and Cytoscape. And for the medium one, pandas and QGraph, which is the NVIDIA version of network X, Plotly and Cytoscape again, and we're doing one version where we're doing just pandas and straight into the graph history render. And for the large one, we're doing, this, as you see, pandas, QGraph, and Gephi, just to show that you can do this on your own. So the data set we're using, it is a data set coming out of the University of West Florida. It's open, it's public, so you can run it yourself. It's basically seek logs, so network logs for that, where they simulated attacks. And the full paper as well, how they do it, is out there. So it's scripted, so it's not like, it's not real, because you can see that it's scripted, because they ran, like, they timed the attack, so you should do that attack that hour, wait 6 hours, run it again, 6 hours, run it again, and a randomizer inside of it. So you can see it's like, it simulates an attack, but it's real attacks they're doing using, Metasploit and stuff like that. So this is what the logs look like. And what we're going to focus on to build our graph is basically looking at the IPs from, you have the source IP and the source port, and the destination IP and the destination port. That's your connection. And everything else that's relevant for this becomes a property on either the edge or the node. So time is a property, so you can filter on time and visualize how things progress over time. So when we take that data set and turn it into a graph, it becomes quite large. 400,000 nodes and 500,000 edges. As you can see, when we look at this image, it shows us something straight out of, like, just looking at it, we have a lot of clusters. And then you start to drill down. That's what we're going to try to do now, like cut into it and look, okay, when we focus on smaller clusters, what do we see? If we go a little bit bigger to the medium graph, what do we see? And back again at the large graph. So yeah, handing it over to Manfred now to take you through that.
Yeah. So one thing I find very interesting about this is if you're wondering what weeks of network logs look like if you just put it into a graph, that's what it looks like. So that is raw network logs. It's something that you normally wouldn't pay very much attention to, but it turns into a very pretty picture, which I quite like. But as Sindre said, this might be pretty, but it's not very useful to us, really, is it? So how should we approach it then? So the answer to that is cutting it down. So what we're going to do is we're going to find a thread, find something in order to grab onto, so that we can start doing an actual investigation on this graph. So these are the goals that we have. I mean, this being let's call simulation of a security investigation. We want to understand how the attack progressed, what vulnerabilities are exploited, and the extent of this attack. And let's role play a bit. Let's say that we got an alert and data is being exfiltrated. One thing special about this data set is that it's already been tagged with MITRE attack labels. That's helpful. So let's just try by looking at the edges, which are labeled as exfiltration, and then see what happens. Just try to pull a graph out of that that is composed of just the edge and the nodes connecting to them. And Sindre was talking about GFQL, so just like databases have SQL queries, graph, GFQL is one of the query languages, and that is how you will specify that query in GFQL. It's quite short, as you can see. And this is what you get. So this is our small data set. So a few notes about how this was built, because I want to make sure that you guys understand how you would go about doing this on your own data. So this was built using, taking the data from pandas, and then doing a layout, and then putting it into a renderer. So that's generally how I like to think about things. I mean, there are some software programs such as Gephi that can do multiple of those things at the same time, but thinking of it this way lets you pick the best options for each. In this case, I have used as layout the Kamada Kawaii layout. I can never get that right. Here I have picked some color encodings. For graph, it's important that you first pick the right node encodings, you pick the right node mappings and edge mappings, and then you pick the encodings. Now, quick note about node and edge mapping. So, I mean, you're probably familiar with, network graphs where you see, one PC here, one PC here, and a router here, and then you have lines connecting them. I mean, that's something that, congratulations, you've been using graphs and you didn't even know it. Yeah. However, nodes and edges do not have to map to physical entities, physical devices. So this is actually something that we're taking advantage of here. We're mapping it to whatever makes sense and trying to answer a question. Here we're mapping it to IP port. Another note about reading the graph, so you can see the edges are curved. So this is actually a standard, way to encode direction in edges. This is quite clever because it means you don't have to take up something like color in order to tell you how an edge moves. So how you would read it is you'll start from the source, and then, I mean, you can think of it goes clockwise, so you follow the hands of a clock down to the destination. Right, so here we're encoding IP as color. There's got two IPs here, great. So that if we're trying to read this graph, that means that there's only two computers involved in this exfiltration subgraph, which is good. So what can we learn from this? So there's the thing. So great. So we've only got two IP addresses involved. Good. Looks like data is only being extracted from one compromised machine, which is the blue one in the middle, to another machine, which is all the red ones. And the red one's using lots of different ports. I mean, that's why you see a big cloud around it. And the attacker is only targeting a single port on the target machine. That's good to know. So you can read all of this from this one picture, which is kind of interesting. Great. So what now? So we said that one of the goals is to understand the extent of the attack. So one way we can do that is to let's find the blast radius from the compromised IP address, and we can do that by isolating the graph starting from any nodes with the IP address of the compromised computer and then moving outwards. If you're looking at this and wondering why reverse, that's a simplification, but that is not important. You'd probably want to do something undirected instead of reverse if you were to do this for real. And that would be the GFQL query associated with that. So great, we've got another graph. So a few notes about how this thing is built. Again, this is with Sidescape.js. Something's different this time. Instead of using Network X with their layout, I'm using at this point I'm using another layout from cuGraph, and you'd probably want to start getting into GPU accelerated layouts at around even around this point would be fine. You can, and obviously you can use these layouts which are designed or useful for larger scale graphs or smaller scale graphs. There's nothing wrong with it. Sometimes it's not. Sometimes it's not entirely necessary, and sometimes you can get a better result with using a different algorithm that's more precise, like the last one that I used. Yeah, so let's start reading this one now. So again, we've got two different IPs still. That's good. So there's no other machines involved in this exfiltration. And here we've got the red ones being the attackers again, and the blue one being the victim. Same thing for the edge curvature. So what can we learn from this? So one thing that we learned is that there seems to be only two ports involved on the victim's computer. So 4848 and 445. So what's the significance of these ports? I think that's a natural question to ask at this point. So port 4848 just so happens to be the Glassfish administration channel. So that would be the administration to access the console and all that. That's not good. And port 445 is SMB. So that would explain why that's involved with exfiltration. They're pulling data out of that. So we've been coloring nodes by IP so far, but one thing that was good to keep in mind is when you are, I think we've pretty much learned all we can from our current set of encodings. So when you're finished learning everything you can, then what do? You change encodings or you add new ones or whatever. So you're building your node and edge encodings. So I mean that could be color. We've been using color so far. It could be size. It could be position. It could be a whole host of things. And these basically correspond to columns in your database. So since we've exhausted this graph, well, let's try adding edge encodings. And we've got MITRE attack tagging. So let's try putting the MITRE attack tags on the edges and then see what we can find. And this is a result. So nodes encodings, same thing. Edge encodings, that's a new one. So you can see that all the orange stuff, it's going to the port 4048. So from that we can conclude that they were trying to pull credentials out of the Glassfish somehow. And we've got a whole bunch of other tactics going to port 445. And just because I can't zoom in, but I can tell you that exfiltration is going to 445. So that makes sense, and it also tracks with what we were seeing before. Yeah, and the interesting thing is both of these attacks are being carried out by the same IP address, so the same attacker. So they're trying multiple different options. So there's one other thing we can do. So recall that network logs are time series data, and we can take advantage of the fact that it's time series data. We can also add yet another encoding in a way. We can try to animate the graph so that you can see the attack progression over time. So this graph tells you what happened. Now we want to know how it happened and when it happened. So this is an animation done with, okay, so the tooling here is still, it is still cuGraph to Cytoscape.js, and Cytoscape.js, I'm using it with Plotly, so I'm using Plotly for some sort of the glue to hold it together, as well as do the animations and the interfaces and such. So this is what happened to the network over roughly 1 or 2 weeks. So you see it start off mostly hitting 4048, which, if you remember correctly, is that one is access credentials, and then hit it for a week. Did a little bit with 445, gave it a break for about another week-ish, and then it's hitting it again later on. So it waited a week and then started hitting again. And if you think of pictures worth 1,000 words, what's a video, right? Now we've essentially taken a look at the way these machines have been running for like a few weeks now, and it took like 10 seconds. And hopefully it should be clear that this is quite intuitive. You can see what's happening, and it's not incredibly difficult to understand. So this is supposed to make your life easier. So since we're Graphistry, we have to plug Graphistry just a little bit. So this is the same thing built using our tool. And pretty much you're getting the same information out of it. You've got a time bar now, cool. And something else that I can try, I'm gonna switch out of that for a second. Try playing with it live a bit. So one thing that you can do is you can drill down to the to a very fine level. So you can go down to the hour now. So yeah, now you can interpret your logs to however level of granularity you like, which is kind of interesting. Okay. Skip ahead there. Okay, cool. So now let's return to the big graph. So we've learned quite a bit over the course of this investigation. Great. Now, how can we use what we've learned to make this more readable? And a note about how this was made. This is a Gephi graph. When you've got smaller to even like medium scales, you can use something like Cytoscape. And the reason I used Cytoscape before is because it is extremely flexible. I can choose how things are rendered very precisely. With Gephi, it's an all-in-one solution. It has layout capabilities, but I didn't use them. But it also has a render which is capable of, I believe they advertise up to 1 million nodes. And so that's just how this one was built. So we saw before that there are 2 ports which are very interesting to us. So why don't we just try coloring them and seeing what we get out of that. So that's the graph. If you'd like to take a guess where in this graph we were looking at before, port 405 traffic is red, and if you guess the little blob at the bottom with the massive red spot, that's that. So that's kind of cool. So you can pick out almost immediately, this made it obvious where in your network's having the issues. And so red is port 445, blue is port 4848. But if you notice something else that's interesting, there's a lot of blue and red blobs going on. So if you're wondering if that is a problem, it is. In our hypothetical scenario, if you just got an alert for exfiltration, now by finding patterns in the data and then applying it to the entire network, now you've discovered a host of other problems which are seemingly disconnected from the initial problem. And I can tell you because we know exactly what happened here. The other machines were also compromised. There's no exfiltration on them yet. That's all. So there's a problem on one. There's an emerging problem on everything else. So yeah, that's interesting. You can see from one picture exactly what happened and pretty much what you need to do to shut it down. Yeah. So one thing that we can also try out. Whoops, I'll leave that for later. I want to give you an idea the speed difference between GPU acceleration and not. So this is the large graph that you saw there earlier. So this is running in this is running on Graphistry. So it's taking about like so it's doing a layout in real time. That's cool. I can change that. And it took like 5-ish seconds to render. Whereas try with Gephi. Okay, no, I'm going to keep talking because it's going to be a while probably. So yeah, about layout algorithms. Actually, I mean, I did mention that there are a few that can be used. I would just recommend just going with force-directed one for general purpose, and for other ones you can use based on specific use cases. Like if you've got a DAG, a directed acyclic graph, then you use a special tree-ish layout and that sort of thing. And yeah, so going back to this, the difference between here is you can see how smooth it is to just pan around and do stuff. And you can do exploration on this too by having access to zoom pen like that. And with Gephi, I just tried zooming. Yeah. It's
And a question there, Manfred.
Yes.
Is this the FPS, like for gamers, FPS?
Yes.
Yes.
Yeah, so if any of you are gamers, this has, if you could think of it in those terms, this has very low frame rate. And to be fair, I mean, we're doing we're doing a preview of the final render, so it will take a while, but it will take a little bit longer because of that. But because we're doing a preview, we have access to features such as curved edges and things like that you'll probably want to interpret your graph anyway. So it makes a huge difference there. Yeah. And yeah, so just because I'm a bit of a graph nerd, I thought it might be interesting to show you guys some other graphs. I mean, if you were to remember on our title screen, we had this graph here. This is quite interesting graph, actually. Just stepping away from security for a little bit, this is a social network. So this is Brightkite, which is one where people checked in at wherever they went, and it went under, and the database is now freely available, which is cool. But it tells you a lot of things about how people are. Going back to the encodings, by the way, previously we were doing a node mapping where each node will have will represent one type of entity. So in the previous, it was just IP port. This is an example of how you can make use of nodes representing two different sort of entities. So in this case, the red one is where people are checking in, and the blue, the blue nodes, which I don't know if you can see, but they represent their average locations. And the blue edges are friendships. So you can actually see from this one picture how people make friends across the world. I mean, you can see that there's a very strong connection between North America and Europe. Less strong, but still pretty strong between North America and Japan, that sort of thing. Another one that you might be interested in. So yeah, this is a biology data set. So we use graph in biology as well. In fact, that's where I got my start with this stuff. We're looking at here, the entities are, the graph nodes represent either genes or proteins or whatever, just stuff. The red ones are COVID, and the blue and orange ones are human. And the difference between blue and orange is what COVID interacts with. So quite a bit. But I don't know enough about the subject matter to say anything definitively other than this is proof that we've studied COVID a hell of a lot. The node size in this case represents the number of connections. So each one of those lines is one study, and there's a lot of lines here. And final one I'll leave you with. So this is a financial fraud data set across Europe. So this is based on the financial reporting the banks do. And yeah, you can sort of see the way money flows through Europe, at least the reported issues with money flowing through Europe. You can see there's a huge band between Latvia and Switzerland. I wonder why.
Yeah. Next one. So yeah, a little bit like how you can use it and why, like what we packaged for you in PyGraphistry, the open source Python library. So getting started is easy. Just go and pip install it. It's out there, and then you get access to a lot of graph algorithms as well that we use. And one of those that we've been using a lot, and it's basically, for me, it's sort of like I've been given a hammer, so now everything's a nail. And that's called UMAP. And I'll try to scroll a bit to get to that one. Yeah. So UMAP, it's one of the algorithms we've been using a lot. And basically, it's clustering. And we used that in a competition a couple of years back where we were given a big data set of alerts. And the task was try to cluster and reduce alert fatigue, basically. And side task, try to find the red team inside of the data set. So using UMAP, you basically, quite easily, you define your features. And so for this case, in an example, you basically say you have your source IP, your user agent, and your event type. And what's happening behind the scenes then is basically UMAP, it treats it as the world's smallest book. And it reads that, and then it compares it to all the other rows of data you have. And it gives you a score of like, yeah, this row is similar to this one, and it clusters them. And if you have something like, and then if you have a new row coming in that does not fit within your cluster, it's an outlier. That does not fit inside of your data. And what we've been doing that and using it for as well is like, okay, if you have a base, basically, say you have 1 hour of traffic, you know that nothing bad happens in that hour, then you can use that, train a model for that specific window and say like, yeah, this is what normal traffic should look like for me. And if you have new traffic coming in, if it fits in one of your clusters, it's grouped in that cluster. Nothing happens. But if you get something that does not fit inside of it, then you create a new cluster and you can do alerting on that like, oh, new cluster, I need to look at this. And also a powerful thing for that, what I've been using it for, I had a case where I needed to investigate someone doing insider trading. So I had 10,000 emails to read. Do I want to do that? No. So I read a couple of them, tagged them as interesting, non-interesting. So I had like a base set of 100. I did not put that into the feature because then I would like supervise it and stuff like that, but I gave it and then I ran it. Okay, read all the emails, cluster the emails that are similar, and then I go and do the encodings and say like, what clusters does actually have any nodes that I've tagged as relevant? What clusters does like, and then you go, oh, here's a cluster of 100 emails that has at least 2 relevant ones. Maybe I shall start focus on that cluster to read stuff and ignore that one that had only irrelevant nodes. And that's what you can do for a lot of this stuff. I've been using it for tracking my financial stuff, basically trying to see what am I using money on, and trying to see, yeah. So basically, that has become a hammer for me, and it's super easy. Like that's all you need. You have your data set, and you create a graph. 1 line of code, or 2 lines of code, sorry. So it's super easy, super powerful, and that's stuff you can run. And everything, there's a reason for Manfred bringing his desktop because we're running it locally. So he's brought his GPU. So if you have a gaming rig, you can run it on that. But and that's the NVIDIA stuff. So yeah, this is, as I said, like this is super powerful and it's open source. You can do whatever you want. And if you want to use Graphistry to visualize it, you can sign up for a free account as well. We have that, so you can we host the GPU. And note to everyone, like if you're doing something super secret data, don't send it to our server. Like it's our server, but it's free to use for you. So I've been using it a lot prior to starting working as well, because then just anonymize your data, and then as long as you're good with sending data to that server, then we don't care. We're not looking at it, but compliance basically. So it's free. That's free to sign up for, and everything you can do with like the graph algorithms and graph analytics, that's a repo. And I guess a lot of you are using Claude Code or something similar. We have skill files as well, so you don't need to learn how to do all those encodings. And I love that because that's painful to know how to do that. So now with skills and agents, you can basically just tell it what to do.
Yeah, and actually a note on that. Sindre mentioned that there's a Claude skill agent that we can use to run Graphistry, but something about all the graphs that I generated with that I just showed you, most of that was vibe code, because so there was traditionally a problem with graphs in that you kind of need a developer, someone to help the analyst. But with AI now, that's becoming a smaller hurdle, not necessarily eliminated. But you'd be surprised how long you can let it, just vibe until it breaks, and then you have to fix it.
So yeah. Questions?